Welcome back. Today we're going to look at exercise 8, which is a very basic wind tunnel test, all right, on this fictitious jet aircraft. So what we're going to do is we're going to set it up. We're going to put the PSI, which I already calculated, the front PSI airflow that's striking it will be about 300 PSI. And that should give us a Mach speed of around Mach 2, or nearing Mach 2, okay, which is twice the speed of sound. So that's Mach 1 is 700 and around 760 miles per hour. Mach 2 is more in the, if I recall, it's getting near the 2,000. It's just under 2,000, like 1,800 or something, if I recall correctly. I might be wrong. You could always Google it. So we're going to see how to set this up. This is computational fluid dynamics, not all that dissimilar from our ball valve. We're going to set this up just like you see here. And we're going to be able to go in and we can change it from pipes to balls and hit play and looking at the different views, how it pierces through the air. In this light version that we're using initially for this exercise, we're going to first set it up in that, and then we're going to bring it over to the full-blown version. Now, again, you have to have professional, SolidWorks professional in order to do this. Those of you taking my class have it. So if you don't see this option in there, then let me know, and I'll send you the proper college license key. But let's go ahead and let's get started. Okay, I'm going to stop this, and I'm going to close this out. All right, so what you're going to do, first of all, is you're going to go to the Vertanu 1 webpage. So type in vertanux1.com. And then you're going to go on this front page to the Brescia, and then Vertanu 2, and the manufacturing 2208. I want you to find near the bottom the jet. Click on jet. Download it, and if you get this message, download anyway, and it should appear. I'm in Chrome, so it's appearing in the lower left. Those of you with Firefox, it might appear in the upper right. But once you get it, you just click on it, and you could from here you could double click on this. Actually, let's go back up one right there, and just grab the whole folder E10 FEA, copy it, and I'm going to put it on my desktop. I'm going to create a new subfolder because I already dropped one in there. And I'm going to go ahead and call this E8 FEA. And then double click on that, and then right click, paste. And it should extract that stuff because it's compressed. You can't just open it directly. All right, now I'm going to restart SolidWorks here because I have that old data in there and I just want to start fresh. You'll find sometimes, this is a little side note, if you're working on the same part and you want to modify it and the original parts are in there, sometimes it's best just close out and restart it. And just so it doesn't pick up on the old models and the changes that you made in the event that you want to discard those changes. Okay, so when you get here, go to Open. And I'm going to go to my desktop, and I created that E8 FEA, and inside there, there's an E10 FEA. Sorry for the confusion. I've rearranged the exercises a bit. That's why this is happening. Okay, now you'll find two things. You'll find the E10 fighter, and then you'll find the simpler fighter B. The E10 we don't want. Okay, that one, there's some problems with it in this latest release, so I'm not sure what's going on, but the simpler fighter B is good. Go ahead and select that. And it should load up. And what you're going to want to do is go ahead and save it right away. Just hit save. Now, if you get any messages about carrying over any sort of data, you should be able to maybe hit no unless it's going to pause the input, or like if it doesn't want to open it, try yes. But I think you should get pretty much what I'm getting here. All right, now that we have that, let's now go to let's see here. Yeah, what you're looking for on solid bodies, hit the little arrow to the left of solid bodies. Now, find extrude 2, right click on it, and click on the eyeball. That will show it. And right click on extrude 3, hit the eyeball. Now what it is you can see if you just click on shell, you can see I basically built a box around this. There is an exercise that shows you how to do this. I took it off because it's really old. I'm not going to make you do it because it's already in here. But basically, when we're talking about a wind tunnel, we're just building it in a box. So with that being said, I created a box, I shelled it out, and then I put caps on it, just like we put caps on the ball valve. Remember, we had to cap the openings so that basically it registers what's inside. So it's shelled out, then I put the caps on. But all we need to do is see the caps. I'm also going to turn on, let's see here. Okay, I guess that's okay. It's strange. The shaded with edges isn't appearing like I hope, but that's all right. Yours might look different than mine. Okay, so with that being said, now we could set this up. So I want you to go to the, let's see here, evaluate. Make sure you're in the evaluate tab. Go to Flow Express Analysis Wizard. Now there is a full version of Flow, again, that we might use. Now in this case, unable to convert, go ahead and hit OK. It's just saying it can't convert the old data. All right, so we're going to start fresh here. Hit Next. And hit View Fluid Volume. And it should just turn into a blue box. If you got that, that's good. It's the internal volume that you're measuring. Remember, if there's any opening, a real opening, then this isn't going to work. You have to encapsulate whatever you're doing. Like before with the ball valve, we were testing inside the ball valve, so the ball valve itself was encapsulating, and then we put the caps on. In this case, we're trying to test the flow on the outside of an aircraft, so we actually have to make the wind tunnel just like in real life, almost like this. Okay. You can hit Next. All right, now fluids. Make sure you select air, and then hit Next. And then the pressure, let's see. Actually, we're going to go with mass flow rate. And you can see pounds. Go ahead and type in 300 pounds. And now rotate this around and select this face, because that's coming in at the aircraft. And I pre-calculated that, like I said, that brings us to around Mach 2 conditions. In the full-blown version, you have the ability to make all these adjustments, but in this light version, we don't have that, unfortunately. We can't just say, oh, here's the speed like per second, so we don't have that in miles per hour here. So we're just going to go with mass flow rate in this light version. Okay, now it's looking for the pressure. So the pressure opening is in the back, so click on that. And 14.69, that's our barometric pressure here on Earth. All right, if you're doing it on the moon or if you're doing it, on Mars, it's going to vary greatly. All right, go ahead and hit Next again. And now just hit Solve. And it might take a while. Like this is a complex model. Depending upon your microprocessor in your computer. Beware, mine might work a little bit faster or considerably faster. I'm working off of 32 threads, 16 cores. I have the Ryzen microprocessor in here, and this can take advantage of all those cores. Okay, so again, if yours didn't finish up, remember, you might only have 4 or 8 threads running, so it could take 4 times as long in that case. All right, so here we could actually see the bands, okay, or the pipes as they call it. You could hit play and see how they travel, and they bounce off like they're bouncing off the windshield, and they're going around the aircraft. Now, if you hit stop, you could change it to balls and increase it to maybe 40 or so. And then it's good to look directly from side or top views and hit play. Now you can see here the velocity, inches per second. Now, we're looking at 35,000 inches per second. And now I actually went on here and so for example, if I put in 31,000 inches per second is equal to 1,761 miles per hour. Now, if we look at the Mach speed, all right, so what were we at, 1761, and we do miles per hour, is equal to the speed of sound. So actually it's 2.2. So that's almost 2.25 times the speed of sound. So it's Mach 2.25. All right, and the conditions would have to be 68 degrees. That's what we had to set to. See, 768 miles per hour is for Mach 1. And when you're talking about these Machs, these speeds, this is what's really fascinating. What you see, because of pressure drops and increases with that high pressure, you create this very similar to what you have occurring in an air conditioner. Okay, you have a very cold area, very hot area, what they call a heat exchanger. And so when you actually see this, I will put aircraft. And we should be able to see some pictures. And there we can see some images. When you're going at these speeds, like, you can actually see what's happening there. It's creating this cloud around it. And that's the condensing of the air. Just like they have what's called a condenser in your air conditioning unit, where you have hot and you have cold. There's high and low pressure zones occurring there. So that's why you get these types of effects, which are just like stunning to look at. Like in some cases, like in this case, emerging from the shockwave, I didn't actually think that the B-52 was a supersonic capable craft. I don't think that's possible with that. Usually you need something more like the Delta Wing or what we see with typical aircraft. So I'm not sure about that one. And again, you don't need to go supersonic in order to get that pressure wave, but it's just interesting stuff. So what you can see around here going on. All right. Now, if you go here to the top view, you could actually see the flow around it. And so that's pretty much all you get with this light version of the software, is to actually do what we're seeing here. Okay, what we're going to do next is we're going to go ahead and we're going to save this, and we're going to try and open it up in the full-blown version of the software and see what additional data we can extract. Now, be aware, they're basically, one's just a stripped-down version of the full-blown version. This one's free, the one we're looking at, and just very basic data like the velocity here that you could get. So let's hit stop and go ahead and save this, the green check, and hit save. All right, now let's see, go to SolidWorks add-ins and find SolidWorks Flow Simulation. All right, so unable to convert the projects, that's fine. Just go ahead and hit OK. This model has a Flow Express project. Do you want to create new flow simulation project from the existing? Let's try it. Hit yes. Let's cross our fingers, hope it works. Okay, now you can actually see the barrier around it. All right, and over on the left here, what we're going to need to do, we're going to have to run it again. So if you go up to the very top right here, where it says Project 1, go ahead and run. And this is really neat. Watch this. You could have it run from additional processors on different computers. How many cores? Like, I have 32 cores capable of using this. But imagine, maybe I want to have a couple cores running so I could run another package while we're waiting for this to run, because some of these can take incredibly long times. So I'm going to go ahead, I'm going to actually let it go with all 32 cores. And I'm going to go ahead and hit run. Now yours might take considerably longer. Again, not many computers have 32 threads just yet. You don't need it for this class. Okay, if you're going to do this for a living, then I would recommend it. I bought this. This is the first computer I've upgraded in several years to this level. I actually, I could run this off of a laptop just fine. But that being said, oh, by the way, click on this little, what looks like an eyeball down here, and we could see this little project solver. For some reason, it hides it. It used to bring it to the front. I'm not sure why it hides it, but it tells you any warnings like supersonic flow is detected, because supersonic flow is not necessarily what you want for everything. For an aircraft, that's That's its intention. But like supersonic flow can be very wearing on things because friction, heat, thermal temperatures, all can have an effect on how long something's going to last. Going back to that page while we're waiting here. Oh, my solver is finished already. Okay, so we don't really have to wait. But let me just go back to this page here. You'll see here the SR-71 Blackbird, amazing aircraft. And I might have already talked about this in one of my earlier videos. But this aircraft flies at such an incredible fast rate. It has the record for fastest aircraft. It could actually, if they didn't have the structure that was made out of titanium, it would actually melt out of the sky, they say, because it's just, there's so much heat and so many thermal issues. In fact, the skin here that's on here is designed where it's attached and the fuel is underneath the skin. And the claim is when it first takes off and the plane is in a cool state, it's leaking fuel all over the surface of it and down below it. And what happens once it gets into the atmosphere, at supersonic speeds, the heat builds up and the plates on the surface actually expand, closing off that so it no longer leaks fuel. So it's really fascinating to read about that. I recommend there's videos on it. Check them out. Okay, so anyhow, let's go back here so we could just minimize this. Now let's go and hit the little plus next to results here. And the first thing what we're going to do is we're going to do a cut plot. We'll learn how to do that. Right click on cut plots and go to insert. Now it's going to select our front as a cut plot, which it doesn't really give us much for this particular instance. So what we want to do is instead of the front, hit this little arrow here and select your right plane. Now you could drag it left or right, but you don't have to. There's actually an animation that will automatically pan both ways. You have the ability to select display for isolines, vectors. You could add a lot of different data points in here for different things. Now, notice right now we have pressure, but let's go with temperature of the fluid. Now, fluid can be described as air too, okay? So just be aware, computational fluid dynamics deals with liquids and airs, things like that. So let's set that for the contours. The isolines, we could stick with pressures on that. And vectors is velocity. All right, so we're gonna get a lot of data off this. Go ahead and hit the green check. And here we can actually see, all right, like we have buildup of temperature right there. Look at that. It's actually, our temperature was 69 degrees. So here we're getting some red, which is indicating it is in Fahrenheit. Now, if yours isn't in Fahrenheit, you just double click on it and it brings up the options here where you could actually specify that. Let's see where it is. Maybe it's not in there. Never mind. But so we're only at about 81 degrees, which is surprising. I would have expected a higher temperature down below there. But let's see what the friction is, what type of friction is occurring here. All right, so let's see, that's temperature. Oh wait, I'm sorry. I was looking at the pressure. That's pressure, okay. So it's 81 PSI right there. And then it's dropping, it's raising, it's dropping, doing all sorts of neat things. Here's the temperature. So we see we're getting close to 500 degrees on certain surfaces of that. And that's not even including really the friction on the surface of the aircraft. Okay, so now if you want to animate this, find that cut plot one, right click and hit play. And it will scan through the whole part so you could see what's going on with it. Go ahead and right click on that cut plot and stop. All right, now let's take a look at another option here. So let's go down, let's go to surface plots, right click on surface plot and insert. Now let's check the temperatures on these wings and on some of the surfaces of the aircraft. Don't do the windshield. The windshield's surface, and I've had weird stuff occur lately, so If you want to try it, you can. Let's get some of these surfaces here, and especially near the nose. Let's get the underside. And any of these little nooks that might have issues getting airflow. And we'll get underneath the wing too. We could even do the wing edge. All right. You don't have to select everything, just a few. And temperature. Let's go with temperature, fluid, okay? And hit the green check. All right, so we see the temperature is getting up to about 533. So it's roughly the same what we're getting because it's the fluid temperature on the surface. So we're getting pretty hot there, okay? You wouldn't want to touch that surface with your hand. 500 degrees, I mean, you know, your oven, you cook a pizza at about 375 to 400. So that's pretty darn hot. Now, also, if you want to see better color adjustments, like right here, double click on this. And let's click on here. You see there's different types. There's even for color blindness, like this. These are for those who have color blindness. Okay, let's increase the scale, the gradient, to maybe 100 or so. And then right here, this will reset to minimum and maximum. And so here you could actually see, oh, that maybe that's not what I wanted. Let me double click on that again. These two, there we go. I think this will give us a better, maybe not. Okay, so we're seeing, again, the variations in temperature. Wow, most of the aircraft is above 350 degrees on that surface. Again, we're going 2.25 Mach 2, basically, just over Mach 2. So that's pretty intense speeds. That's why you have to select exotic metals with, you know, alloys, and basically alloys that can withstand that type of temperature for long duration flights. Okay, let's now go to flow trajectories. Right click, go to insert, and let's go ahead and we're going to select some surfaces that we want particles to bounce off of. Let's get the underside too. All right, now that we have a few of those, now notice we have pipes. Pipes are a little on the boring side. I'm going to go with the arrows flat, but look at all these. You can select whatever you like. The arrows flat's really cool. It's one of my favorite. We could change the transparency on to, let's go ahead and hit the green check. All right, now we might want to actually hide the cut plot. So right click on the cut plot and you could hide. All right, and now we could animate the flow trajectory. Right click on flow trajectories 1, hit play. And here you can see the airflow around it. Now it's giving us the temperature as it goes over, but we know we can double click on that. You can change that if you want. You can go with velocity, temperature, pressure, all those things. And there, the way I got this, I just clicked on the rainbow bar and it illuminates those, which is kind of a cool effect. And we can see the airflow in certain regions. If you click off of it, you can just see it. So we see some interesting things like right there. Look at that. All right. And we've talked about laminar flow and turbulent flow. And right here, we're seeing laminar flow, okay, for the most part. We're not really getting much in the way of turbulent flow anywhere. And that's as should be because it's an aircraft that's designed to cut through the air as efficiently as possible. Interesting note, again, going back to the SR-71 Blackbird, I read an article in an engineering magazine that talked about how they recently ran it through the software just like this. And there was an optimization, which is an AI that goes through and it tries to help you determine how to design something better. Now be aware this SR-71, the original designs were coming out in the late 50s, like 58, I believe, in what they called the Skunk Works when they were developing this. It's very top secret stuff. And when they ran it recently using an AI to try and make suggestions how to make it better, the AI couldn't make it any better. So it's pretty impressive. These guys did this with slide rules. These engineers back in the day with slide rules. Their computers that they had were mechanical in nature. They actually were gear driven, maybe vacuum tubes, but they're extremely primitive. And it's just amazing to think of the technology we have these days. All right, so one more. Let's go ahead and stop that. Right click and hit stop. And now let's go to ISO surfaces and insert. Now, remember that big bubble we saw of it looks like something's going supersonic? This. Let's see if we get that. This, we could go with, let's go with pressure and hit the green check and check out what we're getting there. Now let's animate that. And with it, you have to select the animation, and then down below, it should appear. Oh, hold on a second. Let's see. Right click. You are able to animate that for some reason. I'm not seeing it on mine. If one of you guys figures it out, go ahead and let me know. But basically, I was told, now I'm not an expert on this, on aircraft. I was taught this software years ago, back in the 90s, by someone who was actually working on the space plane, the high-speed plane that actually goes up just above the atmosphere and then comes back down within like an hour. You can make it from New York to California or something like that. It's insane how fast it is. But I am not an aeronautical engineer, so just be aware. But I was told by someone that what you're seeing there is the pressure variations that we saw, that we would witness in something like this. Okay, so what we've seen there is a method. We brought it from the very basic version and updated it, reran it. We were able to extract, we learned how to extract data. Now, when we come back next week, and there's gonna be another video, I'm gonna show you how we're gonna take a computer case, and we're gonna have fan we're gonna put a fan in the computer case and actually be able to select in the software the type of fan, which has all the airflow information. We're gonna have an opening, we're gonna have a heat sink, just like we did for exercise, I think it's 6, where we did heat sink for the microprocessor. We'll have that same heat sink and microprocessor on a motherboard in an enclosure and see how it heats up inside there and where the air is cooling it or maybe not escaping properly, so we could optimize it. So it's really cool stuff. What you're doing here is definitely state of the art. So that, just make sure when you say this, just do an alt print screen, drop it into a Word document. I don't think, let's do a file. If we do a print and save it to print to PDF, let's see if it prints this out as is. I'm gonna drop this on my desktop. Now I'm gonna call this E8 FEA. Oops. Oh, it actually selected my darn. I'll call E8B. All right. Now let's see. Okay, it does it. So again, for your portfolio, that's the type of stuff you want. Okay, this is really impressive, neat things to have. Maybe make a couple images for your portfolio. You just have to send me this. It shows that you did it, okay? And maybe rotate it differently than mine so you're not accidental. So I'm like, gosh, that looks exactly like the one I did. So just be careful. I've had students accidentally send mine to me. Accidentally, most likely it was an accident. But that's about it. Okay. See you next week.